Hi guys, welcome to the next lecture. Today we shall be looking into the basics of probability for a quick brush up. In order to revise basic probability, few terms we have to be familiar with. First, random experiment. What is a random experiment? It is an experiment in which, number one, all possible outcomes of the experiment should be known in advance. Number two, the exact outcome of it is not known in advance, and that is why it's a random experiment. Now, a sample space is a set which consists of all possible outcomes. From a sample space, you can define events. Event is basically a possible outcome of an experiment. A possible outcome of an experiment. Let me give you some examples. Suppose the experiment is throwing a dice. Now your sample space is what all outcomes are possible. All possible outcomes means you can get 1, you can get 2, 3, 4, 5, 6 from a fair dice, right? From this experiment, how can we define different events? One event could be, say, E1. It's the occurrence of an even number. Now, even number means you can have 2, 4, 6. These are even numbers. So occurrence of an even number becomes an event. Another event that we can define here is phi, the event of impossible. So phi consists of no outcome whatsoever. And this is also an event. It's an impossible event. Just like phi is an impossible event, I can also define a sure event. So in this experiment, if I say event 3 is occurrence of a number x such that x is always between 1 and 6, including 1 and 6, that's going to happen for sure. So this kind of an event is a sure event, because this consists of all the possible outcomes actually. Talking of events, we can broadly give the framework for three kinds of events. You can have exhaustive set of events, you can have mutually exclusive events, and you can have equally likely events. What do we mean by all these? So what exactly do we mean by exhaustive set of events? Suppose you have n events, E1, E2, E3, so on and so forth till En. And your sample space is actually equal to E1, union E2, union E3, so on and so forth till union En. Then these EIs are called mutually exhaustive set of events. So it is basically a set of outcomes. It's exhaustive if it covers each and every possible outcome of the sample space. Okay, then only you call it exhaustive. So your sample space will be automatically the union of all these events. Now, what do we mean by mutually exclusive? Mutually exclusive means that if you take two events A and B, now these two events could be mutually exclusive under a situation. Under which situation? If they do not share anything in common. So that means their intersection, mutually exclusive or disjoint, their intersection is equal to phi. Then you will call A and B mutually exclusive events. Now, when would you call events to be equally likely? Two or more events are said to be equally likely if none of them can be expected to occur in preference to any of the other events. So which would mean that they all have the same probability or chances of occurrence. I would like to give you an example here. So suppose you are throwing a coin. If you throw a coin, you can either get head or you can get tail. The chances of while you're throwing, the chances that head turns up is same as the chances that tail comes up, right? So that means these two are equally likely events. Head comes up is equally likely to tail comes up. With all this in our mind, let's define what probability is all about. A probability for any event in classical terms If an experiment results in n exhaustive, mutually exclusive, and equally likely outcomes, and m of them are favorable to an event A, then we can, in this scenario, define the probability or chances of A occurring. That would be equal to m, that is your favorable cases towards A, upon the total cases that you can have, and that is n. So m upon n. Clearly, m has to be less than or equal to n. Therefore, your probability A would always lie between 0 to 1. Few more things that you should keep in mind. Number one, probability of the impossible event is 0. Number two, probability of a complement, everything that is not in event A, will be 1 minus the probability of A. Number three, probability of union of two sets. Now, these sets might not be disjoint. So this will be probability A plus probability B minus probability A intersection B for any AB, okay? Similarly, you can also define probability for the union of three sets, three events. That would be equal to probability A plus probability B plus probability C minus probability A intersection B minus probability A intersection C minus probability B intersection C plus the probability of the intersection of all three sets, okay? All three sets or all three events. This is directly coming from set theory. I hope you can catch up with that. Then it's very essential for us when you are learning about basic probability, what is very essential for us to understand is the conditional probability. So I'm going to talk about conditional probability. Now, what does conditional probability mean? As the name suggests, you have some condition. So some event is happening given something has already happened. So that's the condition. Given that you have two events, A and B, the probability of occurrence of A, given that B has already occurred, that's called the conditional probability of A given on the condition B. This is what is your conditional probability. And when you are looking at the conditional probability of A given B, that is equal to probability A intersection B holding upon probability B, where probability B should not be equal to 0 because it's in the denominator, okay? If it is 0, then this will not be defined. A very quick and simple example. A dice is tossed once. Suppose A is an event of occurrence of 1, 2, 4, or 6. If a dice is tossed once, that means your outcome could be 1, 2, 3, 4, 5 till 6. Anything could be your outcome. And each of these outcomes are coming with probability 1 by 6. Why? Because it's just one value out of the 6 values that can occur. Okay. Now, B is the outcome of occurrence of 2, 3, and 4 or 4. What is probability A? What is probability B? What is the conditional probability of A on B? B on A, both. So probability A, that means what is the probability of occurrence of 1, 2, 4 or 6? Okay, so these are 4 values. Any one of them could come, either or is the situation. So it means that we're talking about any 4 of them can come over the total number possible is 6 outcomes are possible. So 4 outcomes upon 6 outcomes, that means it is 2 upon 3. What about probability B? There are 3 outcomes that you can see here. 2, 3, or 4. So these 3 outcomes out of the total 6 outcomes can occur. So half is the probability. What is the probability of A condition to B? It's going to be probability A intersection B upon probability B. We have probability B. What is the intersection of A and B? Clearly, the intersection of A and B is equal to 2 or 4. Okay, 2 or 4 is the intersection. So which means that 2 outcomes out of 6 outcomes is the probability of this intersection upon, already you know what is the probability of B, it is 1 upon 2. So that means you have 1 upon 3 upon 1 upon 2, that is 2 upon 3. So the probability, so probability A is 2 by 3, and in fact probability A condition to B is also 2 by 3. Lastly, probability A, B condition to A. Probability B condition to A will be probability A intersection B upon probability A. Well, we already know what is the probability A intersection B. It is now 2 upon 6. And what is probability A? Probability A is 2 by 3. So which means that what I'm going to get is 2 cancels, and 3 upon 6 is what you get, that is 1 by 2. Well, probability B is half, and probability B condition to A is also half. Probability A is 2 by 3, and probability A condition to B is also 2 by 3. This is a very special kind of a scenario actually. This is a scenario where occurrence of B has no impact on occurrence of A. The probability is not changing. Similarly, occurrence of A has no impact on occurrence of B. The probability is not changing. When this kind of a thing happens, when probability A is same as probability A condition to B, that means A and B are independent. That can only happen when both these events are independent of each other. So this gives you a scenario that there can be events where there can be events which are independent of each other. Okay. Well, before we get on to that, I want to talk about something very, very interesting here, which is and very important from any exam point of view, any entrance point of view, and that's the Bayes theorem. Bayes theorem is a theorem which basically deals with total probability. Okay. So it happens in a certain scenario when you're able to partition your sample space. So what exactly I'm trying to say here? In order to understand Bayes theorem correctly, you got to understand the theorem on total probability. Now, what is total probability? When does it, come into picture? So if you have B1, B2 till say Bn, they are exhaustive and mutually exclusive events such that the probability of each is positive. So they are all, occurring. And A is any event in between. A is any event. Okay. Then the probability of occurrence of A would be dependent on the probability of BIs. So therefore, the probability A will be the sum of probability of A condition to BI. So condition to each BI basically, okay? I goes from 1 to n. Into probability BI, because there's a probability attached to occurrence of BI. So what we are trying to say here is it will be something of this sort. So suppose you have just 2 events, B1, B2, just the partition is of, 2 events. Partition means that your sample space is basically just B1, B2. Okay, you can divide it in B1, B2. Then if you are looking at any event A, the probability of A is probability A given B1 into probability of B1 plus probability A given B2 into probability B2. Let me give you an example so that this becomes very clear to you. Suppose we have a situation where there are two bags, B1 and B2. Now, B1 is a bag which consists of 2 black and 3 green balls. Whereas B2 is a bag which consists of 3 black and 2 green balls. A dice is thrown. If an even number appears, a ball is drawn from B1. Else, if an odd number comes up, a ball is drawn from B2. What is the probability that the ball drawn is black in color? Well, this is a situation. Now, since the black ball can come out of bag 1 also, and it can come out of bag 2 as well. Therefore, the concept of total probability will be applied here. Okay. So let me define some events. Suppose A is the event that black ball is drawn. Okay. The ball drawn is black in nature, in color. A1 is even number appears on the dice. A2 is odd number appears on the dice. So when even number comes, you use bag 1. When odd number comes, you use bag 2. So therefore, I'm talking about even number, odd number here. Clearly, the probability of A given an even number appears. An even number appears, that means bag 1 is used. What is the probability of A? A means that the ball that you have drawn is black. Black ball from the first bag. So that is 2 upon 5. That is clearly 2 upon 5. What is the probability that you draw a black ball given A2, that is an odd number comes up? That means you pick up the second bag, okay? That's going to be 3 by 5. So in total, what is the probability of drawing the black ball? That's going to be probability of the ball being black given A1 into probability A1 plus probability black given A2 into probability A2. So that's going to be 2 by 5. Now, what is the probability that you get an even number? The probability that you get an even number is 3 by 6, because there are 6 numbers. 3 are even, 3 are odd, right? So 3 by 6, that means half. I can directly write half actually here, plus 3 by 5 into half. So it's going to be half. So probability that you fetch a black ball, the total probability is half. So now you have to understand when will you use the concept of total probability? When some event could be attained under a situation of, say, 2 or more events having been occurred, okay? Then you use total probability. And wherever you use total probability, the next step is for conditional probability, you will be using something called the Bayes theorem. Okay, so till now, we know that if A and B are even such that probability A is strictly greater than 0 and probability B is also strictly greater than 0, then probability A condition to B is simply probability B condition to A into probability A upon probability B. So what has just happened here? What has happened here is that probability A intersection B, we have been able to write it down as probability B condition to A multiplied by probability A. And where are we getting this from? See, you all know that probability B condition to A is nothing but probability A intersection B upon probability A. So if you want to figure out what is probability A intersection B, this goes here, gets multiplied, and this is what is called the multiplication rule. You can apply that here, and this is what you will get as probability A condition to B. Now, when is this happening? What is the scenario? This is a scenario where B is an event that could be attained from different scenarios. As in, probability B is the total probability of occurrence of B under the scenario when A1 has happened, A2 has happened, A3 has happened, some other events have happened. In other words, if A1, A2, so on and so forth till AN are N mutually exclusive and exhaustive events with probability AI strictly greater than 0, that means there's a surety that these events are occurring. And A is any event such that, again, it has a positive probability. And then you can find out the probability AI condition to A. And that's going to be probability A condition to AI multiplied by probability AI holding upon summation of probability A condition to AI into probability AI, where I will take all the values from 1 to n. So this is the total probability. This is nothing but what you've done here is using the multiplication rule, you have probability AI intersection A upon probability A. Probability A is the total probability because the occurrence of A could happen under different scenarios. It could happen under the scenario of A1, under the scenario of A2, so on and so forth. So therefore, probability of A will be the total probability. Let's understand this with an example. I'm going to continue with the previous question where we had two bags B1, B2 containing black and green balls. And then a dice is thrown. If you get an even number, you will use bag 1 to pick a ball. If it comes in odd number, then bag 2. Herein, if I additionally now ask you, in the previous question I asked you, what is the probability that the ball drawn is black? Now the question is, if the ball chosen is found to be black, what is the probability it came from bag 1? How would we actually work in this question? Well, clearly something has already happened. So that means what we have to figure out is a conditional probability. So what has already happened is that the ball is black. So given that the ball that, what is chosen, it turned out to be black, which means A was the event, remember? A is the event that the ball is black. We are to find what is the probability that it came from A1. A1 occurred. What is the probability that A1 occurred? Because when A1 occurs, then you use the bag 1 to collect this ball, okay, to take this ball. So this will be equal to probability A condition to A1 into probability A1 whole thing upon probability A. Now probability A, black ball, you can get the black ball when A1 occurs or A2 occurs. In both the scenarios, you can actually get the black ball. And that is why you are using the concept of total probability here. So A condition to A1 into probability A1 plus probability of A occurring given that A2 occurred. Into there's a probability attached to A2 occurring. This entire thing, the denominator that you see here is probability A actually, okay, the total probability. Well, just put in the values out here. You already have the values from the previous question. Just look into your register and do it. So it will be 2 by 5 into 1 by 2 upon 2 by 5 into 1 by 2. This was the total probability that we already had. 3 by 5 into 1 by 2. So half in the denominator, half of cancels, and what you will be left with is 2 by 5. So 2 by 5 is this probability. And this is what is called your Bayes theorem. Bayes theorem is just a name of conditional probability, wherein the concept of total probability is to be used. And when the concept of total probability is to be used, automatically the multiplication rule is used. And that entire scenario is called the Bayes theorem. Let's use an example to understand the multiplication rule that I've been talking about in this respect. A bag has 5 red and 3 green balls. A ball is drawn at random. Its color is noted and is replaced with 2 more balls of the same color. This process is done 3 times. What is the probability that a red ball is drawn in each of the 3 draws? Each time, this means the red ball is drawn. Well, so let's call BI, the ball drawn in the ith draw is red. So when you are talking about B1, that means the ball drawn in the first draw is red. B2 means the ball drawn in the second draw is red. B3 means the ball drawn in the third draw is red. Okay. And of course, there are 3 draws. So I goes from 1 to 3. What are we interested in? We are interested in the probability that I get a red ball in each of the 3. So that means I'm talking about the probability B1 intersection B2 intersection B3, because that means B1, that is the first draw, I get red, intersection stands for and the second draw stands, I get red, and the third draw also I get red. Now, this would be equal to the probability of B1, the probability of B2 given B1, because see, things are changing. When you get on the first draw, you get the red ball, that means you're adding 2 more red balls to it. So the probability automatically will change. So there will be an impact of B1 happening for B2. Similarly, there is an impact on B3 of occurrence of B1 as well as B2. Both will create a different, both will give you, because of the occurrence of B1 and B2, you will have a different probability for the third time when you are, when you draw a ball. Okay. So this is what is the multiplication rule. And hence it will be equal to the probability in our case. So what do we have? We have 5 red, 3 green. So first draw, I get 5 upon 8 is the probability of getting a red ball. But now what happens? I'm going to replace, I have a red, so I'm going to put 2 more red. This one and 2 more red. That means in total I get 7 red balls. 7 red balls, and of course my total number of balls have also increased. The total number of balls have now become 10 instead of 8. So that's this conditional probability. Now, due to the occurrence of B1 and B2, I've already added so many balls, right? So in total, I right now have 10 balls. Okay. But now again, since, I took out a red ball, so I'll be putting in 2 more red balls. So that means this time the total number of balls will be 12. When I'm taking out the third time, the total number of balls is 12 and the total number of red balls is 9. So this will be your probability, and this is what is the multiplication rule. This probability will turn out to be 21 upon 64. The last thing that I want to discuss in this recording is the concept of independent events. When can you say that A and B are independent? You know, A is independent of B if occurrence and or non-occurrence of A is not dependent on the occurrence or non-occurrence of B. Then we can say that the 2 events are independent. And in fact, in one of the examples above, we could realize it also. So what's going to happen here is that the conditional probability, suppose we are looking into the probability of A, condition to B has already occurred. Now, there is no impact under the concept of independence. If they are independent of each other, there should not be any impact of occurrence of B, right? So this should be equal to the probability of A itself. Similarly, if you look at the conditional probability of B condition to A. So A has already occurred, but there should not be any impact on B of it under the concept of independence, if they're independent. So the conditional probability B condition to A is simply probability B. And if you open this up, you will get the general formula that we generally use. What do we use? So the conditional probability is probability A intersection B upon probability B. If this is the conditional probability, if B is the condition, equals to probability A, and that gives you the probability of the intersection should be equal to the product of the respective probabilities. And this gives you the formula to independence of two events A and B. It's an if and only if situation. If this happens, then A and B are independent. If A and B are independent, then this will definitely happen. From a pack of 52 cards, 2 cards are drawn one by one without replacement. Let's define two events. A1 is the event, first card drawn is a spade. And A2 is an event, the second card drawn is a spade. Now we have to figure out if A1 and A2 are independent. For independence, we've just learned what we actually have to do. So let's figure out what are the respective probabilities. So we would require probability of the event A1, that is, you're getting the first card as spade. So 13 out of 52 cards are spade, right? What is the probability of A2? The second card is a spade. Now the second card is a spade would depend on the first card. Why? Because it's a without replacement case. So when you are drawing your first card, it might be a spade or it might not be a spade. So there's a possibility that you are getting something else and not a spade, right? So 13 out of 52 is for a spade, then 39 out of 52, that means is something else, not a spade. Okay. Now, probability A2, that is the second card, turns out to be a spade. It depends on what result you've had previously. So it depends on whether previously you got a spade. So it's a conditional probability, probability A2 condition to A1 into probability A1 plus probability A2 condition to A1 bar, that is the complement, into probability A1 bar, that is the complement. That is, it's a total probability under the situation where you did get a spade or you did not get a spade. Okay. So which means it will turn out to be 12 by 51. Why 12 by 51? Because in case in the first go, also you got a spade, that means one spade is less now. Out of the 51 left cards, 12 are spade. So 12 upon 51 into what is the probability of A1, that is of a spade, it's 13 upon 52 plus probability that you got something else in the first go and you are getting spade now. So 13 spades are left out of the 51 cards left into probability of getting something else in the first go. So that is 39 upon 52. When you will total it up, you will get 1 by 4 as a result. Okay, so 1 by 4 it is. Now for independence, what do you require? You require probability A1 intersection A2. And we would check whether it is turning out to be equal to the product of the two respective probabilities. So probability A1 intersection A2 is probability A1 into probability A2 given A1. That is the multiplication rule. So, or in other words, it is probability A2 given A1 into probability A1, whichever way you want to see it. So it's going to be 13 upon 52 into, you've also, or you would know that what this will be. This will be 12 upon 51 because one spade has already been taken out. So this will turn out to be 1 upon 70. Now, time to check. What is the product of probability A1 into probability A2? Probability A1 is 13 upon 52 and probability A2 is 1.4, which clearly is not equal to 1 upon 17. That means, therefore, A1, A2 are not independent. A1 and A2 are not independent. Okay. Last question for the day. An unbiased coin is tossed. If the result is a head, a pair of unbiased dice is rolled and the number obtained by adding the numbers on the two faces is noted. If the result is a tail, a card from a well shuffled pack of 11 cards numbered 2, 3, 4, so on and so forth till 12 is picked and the number on the card is noted. What is the probability that the noted number is either 7 or 8? Well, so you have to find out that what is the probability that you get either 7 or 8. Now, 7 or 8 you can fetch under the situation of getting, when you are tossing a coin, of getting head or tail under both the situations. Let A be an event of getting head. Let B be an event of getting a tail. And let E be an event that the noted number is 7 or 8. Now, what are we supposed to find out? That the noted number is 7 or 8. Now, 7 or 8 you can fetch under all circumstances. Circumstances as in under the circumstance that you got a head, under the circumstance that you got a tail. So that is, we are supposed to find out what is probability of E, and it is actually the total probability because it can happen under the situation of A occurring. So it's the total probability, probability E condition to A multiplied by probability of occurrence of A into probability E condition to B multiplied by probability of occurrence of B. So this will be equal to, we should actually first find out separately what is probability E1 condition to A and what is probability, not even, sorry, there's no even here, that's just E, okay? Probability E condition to B, okay? So probability E condition to A means that you are talking about the probability of getting 7 or 8 under the situation that you got a head, okay? And what are you doing when you get a head? When you get a head, it is told to you that you roll 2 unbiased dice and you get your outcome is the total number that you get. So, well, when I toss 2 coins, under what situation, under what combinations will you get a total of 7 and a total of 8? So there are 6 positions out of 36 where I can get total of 7. 1, 6, 6, 1, 2, 5, 5, 2, and so on and so forth. And there are 5 positions where I get a total of 8. So 5 out of 36. That means our total 11 cases give me a total of either 7 or 8 out of the total 36 outcomes here. Now, what is the probability of E given B? B is when you toss, your toss gives you a tail. And when you get a tail, then you are, you have, say, some chits with you numbered 2 till 12. And out of that, you pick any and you then note the number. So what is the probability that the numbers are 7 or 8 out of those chits? Well, 2 chits out of the 11 are basically 7 or 8. So 2 upon 11 is that probability. Hence, the total probability of E will be 11 upon 36 into, what is the probability of A, that is getting a head? It's half. Plus 2 upon 11 into half. So this will be equal to 193 upon 792 after taking the entire LCM. Thank you very much.